Well, the next presenter is Ray Madachy, and I really don't know what I can say about Ray. He's professor at the Naval Postgraduate School since 2008, and before that, he was a research assistant professor at the University of Southern California. He's got a PhD in industrial system engineering from USC. Barry was a member of his PhD advisory committee, and Ray's collaborated with him over the years, seen him in many distant lands at different conferences. Kind of envy him for that. My friend Ray and I co-authored a book called Software Cost Estimation Metrics Manual for Defense Systems. We had contributions, we edited that, wrote some chapters ourselves, things like that. I just enjoy spending time with Ray. Look forward to seeing him soon. Without further ado, Ray, are you ready, buddy?
All right, Brad, thank you very much. Appreciate that. Sorry, people, I got to be in Brad Clark mode with no camera as well. Bill and Dan, I didn't mean to step in, but that was some very good stuff there. And I just want to say that I've been going to these COPLIMO forums since 1993. And like Barry always used to shepherd the top of the line ideas in the field. I'm glad to see the traditions being kept up. Seriously, you've seen really creative work today. Let me introduce my other co-author, Mike Green. He's there in the chat with no last name, Mike. Now, he's been in our department longer than anybody else. And he has worked in the service and out of the service on these types of combat systems that we've analyzed. One of the very first things he said to me when I joined the department was, you know what, the Navy ought to adopt a product line approach more. So much could be saved. So, we should teach it that way in our software engineering course. He said, you know what, couldn't something like COPLIMO be used to look at these reuse costs? And I said, well, as a matter of fact, we do have this thing called COPLIMO, and that's been the basis of this research I'll try to summarize for over several years of these allied projects that we've been doing. So Mike more or less serves as the domain expert on these types of systems as well, and also some of the new model-based system engineering techniques we've introduced here. So COPLIMO is a framework for constructive product line reuse cost modeling and investment analysis. And by framework, of course, like everything Barry did, it's not just a single fixed instance of a model, nor just can be used for just a single purpose. So this was, we started this effort in about 2003. We've applied it across these case studies we'll show you. A product line we define as, we all know, a set of products that has some common features, and you purposely manage that in a way and exploit that commonality between them. There are different parts of the basic framework here for modeling different types of systems and processes at different levels of decomposition and different system types, whether it be software, hardware, or combined. And we'll see how we've supplanted some of the initial models here with newer cost models relevant to the types of, requirements for the systems under consideration. For the new aspects here for model-based system engineering, and Mike introduced me to this, called, some of you might know this already, orthogonal variability modeling. And this is really handy where we can decompose the system. And once you go through the work, it's just, you can instantly count what you need for the purpose of the size inputs to these reuse models, reuse and investment models. So we've done this on several application case studies, and not surprisingly, they've all showed large return on investment in terms of if one decides to take on a product line approach versus doing one-off systems, it really pays off in the long term, usually just after a few systems, to have done it that way. So this has been funded by a couple entities. The Department of Defense is part of the Systems Engineering Research Center, the CERC Research, and our own NPS Acquisition Research Program. All right, so this slide here shows a bunch. I guess I could talk for 30 minutes on this slide alone. I guess, Mike, you want to do that for me? No, actually we could, but it's showing how the model is extensible in a lot of ways, and also across the different types of applications here in chronological order. We analyzed this types of cruise missile systems, Aegis ship software, cross-domain combat systems, and then last couple have been UUV missions and more specific types. And so we know we use parametric models for this. What are our units of size? Well, that depends on the information we have and how we're modeling the systems. Here we're modeling these cruise missile systems and by the unit of system component, very large components, think of like a radar or a launcher, that type of component. And then some of these we can look down to very detailed lines of code or count requirements interfaces, depending on how we're doing the modeling. And then we all have a reuse model underneath. So we have to differentiate, is this come for free black box reuse? Do we have to modify it extensively, et cetera, and count for those types of reuse categories and other adjustments to equivalent size from which effort and cost is derived from. We have different reuse investment models. This is initial basic COPLIMO, and more recently we've supplanted it for systems engineering reuse with a more modern relevant model here for systems engineering. We've modeled these systems and reference architectures in various ways using OVM, data flow modeling, some other methods, and some SysML methods, requirements modeling, and activity models. For some of these, we were lucky to have actual cost or size or savings, in fact, in one case. And so we had a lot of government data here on the cost of the subsystems that were aggregated to total system cost. Over here, we were really lucky here on the Aegis ship. They actually have a product line of software for that combat system software. So we were able to have actual lines of code by variant. Very lucky in that regard. And then over here, we had cost at different levels of decomposition. No empirical data here. In fact, we didn't need it. Instead, we used relative cost trade-offs afforded by the co-system reuse model. For the purpose of making these investment decisions, we don't need actual costs at that point. So how big are these systems? These are the baseline sizes of the reference architectures from which the variations are changed with respect to. So 20 subsystems comprise a total cruise missile defense system. Baseline Aegis baseline, about over 2 million lines of code. Here we were looking at both software and hardware and those sizes. Here we counted number of actual high-level requirements and interfaces. All right, and so we'll show how we use these. First, let's look at the types of models and tools we've used over the years. When are some of these will look familiar to you? In fact, there's a key here that this one must have been copied from an old USC presentation just because of the, well, where the page header is, the footer. Anyway, basically the initial model was using COPLIMO for software costing of multiple products. And we have a cost model for initial development and for lifecycle extension and maintenance. And so we use COPLIMO for the development cost, and then we added these parameters here for the relative cost of writing for reuse. And for the different reuse categories, we defined some reuse weights for those. And from there, we can derive the costs and the savings of a product line approach. So black box model of the initial version, assume an average size and then adjust that with the COPLIMO 2 cost drivers, whatever cost factors that you have at hand. And then you have to allocate or apportion how much of the product is unique for the mission or the system variation at hand, how much is reused with some adaptations. And here we mean lines of code that are changed, and how much is used black box as is with relatively small effort. And for all these categories, we have relative cost of reuse, which are just weights to the effective size. And then we added this here for the relative cost, the investment cost to make something reusable across multiple products. And from here, the black box tells us how much effort we put into investing in reusable components in the baseline architecture, how much it would have cost without a product line, and then how much we save overall by the variations. And then all these extensions we'll show you have also been implemented for different situations. Here is a version that's more of a high level and accounts for total ownership costs across the full life cycle. It's simpler in that you don't have other cost drivers to adjust like for COPLIMO. So it's more of a top level model. It also assumes here we see average size and annual change costs. It assumes homogeneity of the different product variations, which of course isn't always the case. In most of our case studies, we did not assume that and look at the actual detailed characteristics of the individual variations. But this high level model here applied to systems or software or hardware or both. I have a variety of tools that are web-based and Excel. I'll show you some results from these tools and also where you're going to get these, which is our website, which I should put as a reference. But here's a URL for this particular tool. And we go to the main homepage, you see a few more links to other tools and some of the papers that we reference. So here are some basic inputs here for this top level demonstration where you assume an average cost here, 5 million for the average system. Here's how much we will change per year, 10%, how long and interest rates. And here are the essential COPLIMO parameters. For a product, how much is unique, right, for that particular mission or customer, whatever, how much is adapted from the product line with change, and how much is reused with no change. And here are the relative costs for these categories compared to if it was developed new for the first time for a single product. Adapted is 40% relative cost compared to developing it new. If it's reused, black box is 5% relative cost. This is what goes into the model, as well as the extra cost of developing it to be more flexible here. This means 70% more effort compared to developing just for a single product or single system. And across 7 products, we can see the cumulative ROI goes up pretty higher here with these inputs.
Ray, a quick question. On the unique adaptive reuse percentages, those are for the initial development?
No, the initial development is different. In fact, if you look at column 1 here, everything is different. That's where the only place where we put an initial investment. So these actually refer to products 2 through 7. They're all assumed to have this much change percentages and all the same. So homogeneous that way.
Okay, thank you.
Yes, good question. Yes, I should point out baseline number 1 is different in all regards. Yes, and you get a negative return on investment because of that. Okay, yeah, good question, Jim. Okay, combat systems, deep dive into several case studies here. So we developed a framework here specifically for Navy combat systems based on a reference architecture and then instantiated for different product variations and model this with different MBSE approaches. And so from this, we derive the inputs we need to size up the software or the hardware, count the number of entities, size units. Here's a very generic architecture here, a data flow diagram. Each combat systems needs to detect, control, and engage. And then here's more of a decomposition here, right? You need sensors to do this. You need an HSI, data links, pass the data around. You need weapons to engage. This is a top-level data flow diagram, and this is decomposed more into orthogonal variability models. at different levels of decomposition. From there, we simply count what we need to in terms of the reuse categories. So for a given set of systems, we develop a reference architecture and use OVM so we can look at the variation points for these types of system elements. And in these first case studies here that were cost-based, we identified the subsystems, and then we looked at what are some actual system costs from the government and mapped those to these elements in the architecture models. So these were not parametric size-based costs in these cases. So here's an OVM here for the cruise missile system. And the notation shows here variation points down here, right? And elements of the system, some are mandatory, some are optional, representing what can vary. So at the very top here, let's look at every combat system needs to have a combat system package, and including, you need some sensors, you need an HSI, you need weapons, you need data links. Okay, you need sensors. Well, what kinds? Here are different possible sensors: air search radar, surface search, EO/AR, LiDAR, IFF. These are all different options you have to build a new architecture for a new system, right? Some of these are required, and some of these are, mutually exclusive. Some impose other requirements or dependencies, and that's what the notation displays here. So we decompose the system here into OVM to the lowest level that we need here to populate for cost, basically. From here, we now can classify, if you look at the lines in the OVM, that some of these, if you choose this variant here, an air search radar, with respect to a baseline architecture, that means it's going to be adapted. You have to put in some work here to modify it for your new system. If you would have chose this type of sensor here, that implies you can reuse the product line architecture as is, because the experts say you don't have to modify it very much. So these are the reuse categories. From here, we count the number of subsystems in the architecture and populate the COPLIMO model. So for this cruise missile system product line, here's the average cost of a similar defense system put together with the subsystem costs that are aggregated from government data. And actually, this is 10% based on real world data as well, and actual government interest rates, ownership time. And we ascertained the average product line percentages for these 7 variants of a cruise missile system. This much would be unique, adapted, and reused. Here are the relative costs straight from basic COPLIMO, no other calibrations per se. And use the default 1.7, and we get a whopping ROI here for a cruise missile product line in this case, based on decomposed OVM modeling, and from there we can count how many subsystems are unique, adapted, and reused. That's the cruise missile system. Next one, altogether different, fully software case. The Aegis, an actual system, not hypothetical. So again, we had some real data here, which aren't these 9 round numbers, but we actually used the numbers here. And these are about how big the Aegis variants are for different ship configurations. And we also had, of course, Lockheed Martin doesn't want us to display all the real data, but they were kind enough to also show us their cost savings, which mapped up very well to what COPLIMO came out with by default. Wish we had more case studies like that. Next one for combat systems, cross-domain. So here's an example here. We're looking at air, surface, and subsurface systems, hardware and software components. We applied OVM modeling here. From here we can enumerate how many of the pieces are going to be adapted, reused, unique, the supporting rationale. And here's one of their, we did a probabilistic approach here. Here was the most likely scenario here across these different types of products. So here we have underlying, we have software cost derived from COPLIMO using lines of code from real world systems. And we have the hardware cost derived from actual system costs of these real world systems.
Ray, can I jump in on that?
Yes, please do
Okay.
so, Mike.
All right, let's go back up to the previous slide.
Which one?
The
One
previous,
here?
yeah. One of the issues, this was kind of one of my soapbox issues. This represents, the top one represents the surface Navy, the bottom one represents the submarine force. And the question, I think, no, I guess not, I'm sorry, beg your pardon. They represents all of them. One of my the big things I was concerned about was the fact that there's duplicate effort across both the submarine and the surface navies. They'll go out and let contracts for a submarine system, and they'll do the same thing for a surface system. Two contractors trying to develop essentially the same thing, because if you really get down to it, the variation points are going to be at the front end on the sensors, because a surface ship sonar is a little bit different, and on the back end because the weapons are a little bit different. But for the most part, everything in the middle is the same. And even then, you'll still have reuse across the sensors and the weapons. So my question is, why are we doing it this way? Why, in fact, the whole purpose behind a product line model is to plan for reuse. There's no such thing as serendipitous reuse, according to the experts, which I tend to believe. And I see a lot of this going on in the government. I have for quite some time. So that was the reason for this project right here. If you go to the next slide, what we really kind of did there with the numbers, this is partially based on real numbers also. The students that did this gathered the data for us, went out and got some pretty fair data. And if you'll notice, about the time that we get to number of products in the product line, that we have basically, we're starting to get a positive return on investment. So I just throw that out for your consideration.
All right, super. Hey, we'll show that visually here. Also, when you look at UUV product lines, right here are our use cases here. Again, it's pretty clear here that there's a lot of overlap. These different UUV unmanned systems in general, excuse me, not UUVs, aerial systems as well. There's a lot of overlap, commonality. So why stovepipe the developments, right? Let's exploit the commonality, whether it be airborne or otherwise. Basic use cases are the same underneath, with variations, and these can all be fed into the COPLIMO framework. So here are the defined missions here for the Navy that we use here for this next case study. So the students parse out descriptions here of these defined Navy mission types, generated activity models of the mission operations, and those were used to enumerate requirements and interfaces to populate COPLIMO model in this case here for parametric size and cost. So I guess we would call this the COPLIMO with COPLIMO model. So replace the software model with this reuse for COPLIMO, and we count up the number of requirements and interfaces. The full model, you know, for COPLIMO has algorithms and scenarios. Here we just modeled interfaces and requirements through the activity models. And then we had to ascertain with experts of those different requirements and interfaces. Which of these categories are they? As well as easy and nominal difficult for further adjustments to equivalent size. You get the same type general outputs. Here's the definition of the reuse categories, slightly, well, in the parlance and interpreted here for these UUV requirements in terms of measures of performance, measures of effectiveness, as stated in requirements in the Navy descriptions. And the default weights there in COPLIMO 2.0. And this summarizes the results there based on counting those requirements. And so here is the baseline architecture for ISR mission. And these columns show the difference there between non-reuse size, if you did them all individually, versus the product line approach. So for all except the first one, you have less work to do as reflected in the reuse size, right? And that's all we need to calculate the relative cost and return here. And summarizing across, aggregating these mission types, we get a very high ROI of 5 at the end, using the COPLIMO reuse model in this case. And the last one, just recently completed thesis. Previously, we looked at generic types of UUV missions. Now we are doing a deep dive of mine countermeasure UUVs, the 6 different architectural variants. And this student did a great thesis job here, applied all those same principles for these 6 architectural variants for MCM mission using OVM modeling, and did the same thing here with looking at the equivalent size here using COPLIMO reuse, as well as it's always good to do a sensitivity analysis of the reuse assumptions here. And no matter how you look at it, optimistic, pessimistic, high ROI of a product line approach. And so, bottom line, not surprisingly, what a great framework here to analyze all these different aspects, the trade space, like the other constructive cost models. Here now we're looking at the extra costs here for putting in investment. High ROI. So why do we keep doing it otherwise? On day one, we need to consider the product line approach here at the earliest stage of design and develop reference architectures and exploit the commonality. What next step we want to do is combine this economic modeling with systems effectiveness modeling. That is how effective at achieving our mission needs, in addition to not just the economic aspects. And with that, open to any questions if you have time.
One of my thoughts, Ray, was relative to Mr. Tabor's presentation, was how would a couple of those models fit into essentially evaluating elements of the product line when we don't have any information.
Oh,
Because I believe, if I recall, he talked about the concept of doing feature modeling, which is a little bit different than the way we treat it with orthogonal variability. But
and Brad has an idea too. Yeah. Like the work that we were seeing from Bill Nichols as well. Well, I think we could adapt this framework, as Brad asked.
For everybody's edification, the way we actually do these, we have occasional thesis students, but primarily what we get are what we call capstone students that are part of a section of students that are going through for their master's degree, and we get them for 9 months. So it turns out to be a 9-month project. So it's far more inclusive, if you will, than a master's degree. We get a chance to explore a lot of other things.
I'd like to chime in on that a little bit. One of the advantages of that we have is we have a very stable team over a long
Mhm.
time, and so characterizing, my characterization over a fixed team, and I don't know, if that model would work the same if you had heterogeneous tasks. That would be an interesting question to explore. I don't know if there's anything magical about the particular coefficient that we've got. There's no, when you do the math, it just says there's a coefficient there, but it's, there's nothing to, this is like it's a characteristic of human ability to estimate how difficult something is, and maybe that's what it is, but I don't know how that would how that would change as you move across different tasks, if it's similar or if it's but it's a place to start.
Yeah. That was my point. The other thing that really resonated with me when I saw that is that before I came to NPS, I worked at Lockheed Martin in Morristown for a number of years, and all the baselines for Aegis at that particular point were sequential. Now they are actually running a number of parallel baselines. The variants on the Aegis destroyer, the Aegis Ashore variant, a number of different foreign variants. I was the technical director for the Norwegian frigate, and that was actually the breakout one where we first kind of applied very rude and crude product line ideas. But now it's a fairly sophisticated thing, and I really wonder if we took a look at that, what you've done, and applied it to that, if the numbers would, if it would work the same way, because that is a very stable organization now.
Yeah, I think that's what's important, a stable organization. And do you have estimates and actuals at that level? Because if you do, then you've got a place to start. And it's, you put them together, and if you put them in a spreadsheet and start, looking at the graph and say, does it look right? And you can usually see that right away. If you've done a bunch of these things, you can see, oh yeah, this is this kind of distribution. So and since there's sort of a mathematical basis under these assumptions, you would get this sort of thing. It kind of has the right ring to it, if you know what I mean. It's got that, oh yeah, this is what you would expect sort of thing. So if people behave that way, this is the other question though.
We may get back to you on this idea. I'll talk to my friends at Lockheed and see if they would be interested in applying something like this.
All right, do we have any more questions for our presenters?